Cool. So as you might see, um, homework 3, we'll be doing this musical note classification using CNNs. We will talk about what CNN is, but for now, if you're interested, you can look at the Jupyter notebook that I sent you, which look like something like this. Oops. But basically, what you can do is just to press Shift Enter all across the whole homework. You should be able to get all the result that you need. Pretty much is that you need to rerun the training process so that you get these plots. That's all you need. So basically, you'll go through the whole training progress, which shouldn't take too long on the GPU. Should be finished in less than 30 minutes. So we are just training a very, very simple neural network to classify, the spectrogram of the, well, where is it? The spectrogram. So the input will be some spectrogram. Well, there's no sound. Let me connect it to the. Yeah, so the goal is just to, input some spectrogram, and the output would be, either one of the 11 classes. And you have to figure out what's the right class. And we will be using this like NSYNC data set. Basically, it's just a bunch of short 4-second audio of different instrument at different velocity, different pitch. So it's a huge data set. But basically, you will have figured out how to download it. That would be, I guess, the biggest challenge in this homework is, preparing the NSYNC data set. So either you can use Google Colab to connect your Google Drive in Google Colab so that you have to just follow these things so that you can, mount your Google Drive to Google Colab. So in Google Colab, you only have a very limited amount of local storage. So you have to, one way to fix that is to just mount your Google Drive to the Google Colab. So basically in Google Colab, you can sort of like just access your your Google Drive like this, content drive, my drive, and this just connected to your Google Drive. So you can put the data set in your Google Drive. So the data set will be in some link that's in my Google Drive. So you have to copy these, sort of like copy those to your own Google Drive, and you have to mount it to Google Colab so that you can access them. But after that, you will just like unzip these data set, transzip, validation set, and test set. But basically that's pretty much that's it. So Google Colab, as you might have experienced it, if you run it for, I don't know what's the daily allowance for free account, but for me it's like after 6 hours they will kick you off and you cannot access this again that day. So we will also have the Great Lakes cluster that's a cluster. So somehow I don't have the instruction here. But to look at how to use Great Lakes, you can look at this instruction. So go to homework 3, and at the bottom, or in our course website, there's this computing resource bar. You can look at the instruction. But basically, once you've logged in, you have to do a bunch of things so that you can do this. But basically, Great Lakes is another way so that you can access sort of something like, let me just show you here real quick. So you can request like GPU. I will show you how to do this on Wednesday, but just to give you a flavor if you want to try it. So, I can set up a GPU for 1 hour for 4 CPU cores, for some RAM, and, number of GPU. So once I click launch, I should be able to get something like Colab. But basically what you will be doing is the same thing. Just that the data set is already on Great Lakes. So you can just copy paste those to your home directly, but otherwise pretty much it's the same experience. So this is like starting. Cool. So, once you start this thing, you can connect to Jupyter Lab. So you will get something sort of like similar to what you have in Google Colab. So look at homework 3. Then you can sort of also do this. So this is a Jupyter Lab that's running on the Great Lakes, which is the central GPU cluster or general computing cluster at So you can also run, Jupyter Notebook on this thing. So basically you can run these things and you can have access to GPU. We will go through it on Wednesday, but if you want, you can just sort of like follow the instruction here to try to start doing homework if you like. What else? So if you want, because on Wednesday we will show you how to do Great Lakes. What you can do for now is to create an ARC account so that on Wednesday you can follow us. So, go to this link. I will send you later after class. So you have to send this request so that you get an account on Great Lakes, and I recommend you to do so. Even though you might not need it as that much in homework 3, you can pretty much survive using Google Colab. But once you have this, it will be helpful for, future homework or the final project. If you do want to do something rather than, rely on Google Colab, you can get much better GPUs on the cluster. So what you need to do is I have all the instruction here. So, you just put something here. You have to say, you will put my name here, put my email here, SMTD. Kind of confusing what this is, but I guess just put SMTD and say, accessing Great Lakes for the course, blah, 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 that you put here. And once you submit this, after 1 or 2 days, they will create an account for you so that you can log into this. If you don't have an account, you won't be able to access this page.
What about the bottom at the form?
This one?
Like you need this, I don't need this logo account.
Oh, we need the Great Lakes. Yeah. So this just follow this screenshot, Great Lakes, this thing. And then my name, my email, and SMTD. It's kind of confusing what this means, whether the my name or your department. I don't know, but I guess put it SMTD because your account will likely be linked to our course account. Cool. So this would be the only thing you need to do by Wednesday. If you want to follow us on Wednesday, I highly recommend that. Otherwise on Wednesday, people will be trying Great Lakes and you will be, well, I have no access to the portal. Cool. But if you like, you can also just try it on Google Colab. It takes some time to get the data set loaded. And so this is the sort of like a fun fact of doing deep learning for music is that most likely half your time is on preparing the data set. And the other half will be, actually figure out what data set to use or, fine-tuning your data, fine-tuning your model. But, most of the time will be spent on getting the data set ready. But anyway, 2 options, either you do Google Colab, as we done before, or you can try starting to use Great Lakes, which will have, faster GPUs and, also what's the benefit of Great Lakes, I guess? you don't have, daily limit on how long you can access Go Collab. But the slight downside is that you might need to wait a little bit if you are requesting GPU at, peak hours. But usually it's fine during the middle of the semester. At the end of semester, thing will become more chaotic. Cool. Questions? Oh, you will be provided a bunch of GPU hours. That's the course GPU hours. How long is that? 560 GPU hours. That's the course account. So you will get these for all the assignments and final projects. So use it wisely. If you need more, I guess just let me know. But I think you should be able to do a lot of stuff for 500 hour GPU hours. Because last semester I did like 300 GPU hours. No one actually spent it all, and you don't even have the chance to spend it all because we don't have that much of GPU on the cluster. Cool. So this is ancient data set. We can just look into it a bit. 300K single shot musical notes at different, 1,000 commercial sample libraries with different MIDI pitches and velocities. So it's like 21 to 120, 108. So basically cover the piano range. So for different pitch and play at 5 different velocities. So some of those example will be, well, something. So this is a bass. This is a guitar, electronic one. This is and you also have like keyboard. So as you probably noticed, there's some ambiguity in the instrument. So, listen to this keyboard and, and if you're doing guitar electronics, somehow it could be kind of confusing whether it's a keyboard or it's a guitar. So that's sort of there are some built-in ambiguity of the task is that for certain pitch, for certain velocity, it can be quite confusing even for human to see what the actual instrument is. So at the end your accuracy would be somewhere around 7 to 80 80%. So that should be the accuracy that we are aiming for. If you have better model, you can do, I believe, easily go beyond 80%. And I believe you can also go over 90% a little bit. Cool. Other than that, we will go over it on Wednesday, and it will be due on next Monday. We will think about dynamically adjusting that, but we'll see how things goes on Wednesday. Cool. Any question on this homework? Cool. But pretty much, if you are afraid of coding, it would be sort of like homework 2, even easier than homework 2, is that a lot of it would be, just pressing Shift Enter to give it an experience of, how to do these stuff without actually doing much coding. But if you're interested in how it actually being done, you can look into the Jupyter Notebook. So Jupyter Notebook is a great way to sort of like, go through the code one by one. And at any point, if you're, you wonder what this, thing is doing, you just print it, print such like, X the shape, and then just print it to see what that thing is, or, just print whatever stuff that you have, print your training loss, print your validation loss, print whatever things that you wonder what that is. So that's sort of the goal of Jupyter Notebook. It's not something that you just, you can press Shift Enter and you get everything. But if you want to dig into what each component is doing, it allows you to just write some easy code so that you can run and to check what's going on, to inspect what's going on. Cool. So today we will sort of like finish up our deep learning bootcamp or deep learning 101, which is compressed into three lectures. So it's very tough. But anyway, I guess the idea is not to sort of like make you become like an expert of deep learning, but rather, sort of get an idea what deep learning is doing. So, we would talk about, training, validation, tests, and you might wonder what it is without, actually learning about what those concepts are. And, we would talk about regression, classification, and we talk about, layers, optimizers. So you should have a sense what those nouns mean. And then, we will get a better understanding of what we are actually doing in the class. Cool. So just some recap. So last week we first talked about, some common loss functions for regression. So it's in the simplest form as you can imagine, but in practice, we have to do a bunch of summation and do a bunch of fancy stuff. But the simplest way to think about loss function is just to measure the difference between your prediction to the actual ground truth. So you want to make your prediction closer to your ground truth. So you have to sort of define some way to see how far away they are, and then you try to optimize it. So, this is regression. If you're just doing this, you basically just measure the difference between your prediction and the actual ground truth. So you can do, just absolute difference, y minus y, and then do the absolute value, or you can do square loss. And if you want to do binary classification, you have to do that sigmoid trick so that you sort of like turn this y into something that's close to 0 and 1. So if your output is large to the positive, infinite, your output will be a 1. And if it's like very negative, then you will get the output of 0. So it's sort of like turn like a continuous number into sort of like 0, 1-ish label. So once you've done this, then you can sort of trend it in some way. And so this is the loss function. Look terrifying, but basically what it does is that, look at the loss function. If y equal 1, so y is the ground truth. If the ground truth is 1, the loss function look like this. So, when we are optimizing the neural network, we want this loss to be lower. So it would just sort of like fall onto 1. So the goal of this component of the loss function is to drive your prediction to 1 when your ground truth is 1. And on the other hand, the other component of this loss function is that if the ground truth is 0, then you want to drive the prediction down to the lowest loss value, which is at 0. So, this binary class entropy, even it looks kind of terrifying in its final form, what it does is basically, if your ground truth is 1, make your prediction 1. If your ground truth is 0, make your prediction 0. That's basically what it is. Cool. And now for class entropy, which is for multi-class classification. This is what we will be doing in homework 3. So now, instead of, doing that binary classification, say whether it's a cat or not, now we are trying to figure out, which of the instrument we are actually predicting. So now we, instead of, just doing, 0, 1 classification, now we want to sort of like turn our output into something that sort of look like probability. So what it does is that, these are the maps, but what it does is to map some real value into a bunch of numbers that sum to 1. And that has like relative importance, sort of like something like probability. So basically what you want to do in the, ANSYS musical note classification case is that you want something like 90% the actual instrument that you are aiming for. And, the other stuff will be, 1% each or whatever that is. Cool. Let's just jump this, but basically they have the same form that, you just want the prediction to be 1 for your specific class and 0 for any other class. Cool. So this is sort of like the high level understanding of how we do this training of neural networks. So we build a neural network. So it defines a bunch of functions, and you want to figure out what the best function is. But before that, you have to define what is the best. How do you define the best, and what is good for a function? So that's the goal of the objective function. So the loss function. So loss function defines what's the best function that you're looking for. And finally, you just want to figure out what that optimal parameters is, lead to that best or lowest loss function. I feel like the lighting is actually doing something. Anyway, cool. And we talk about gradient descent. It's just thinking about how we can figure out what's the best loss function is. So the idea is basically at each point, look at how deep it is, and so that you can figure out where you are going. So the slope would be positive here. So we are actually doing negative update. So that's the key of gradient descent. It should be the opposite direction of your slope. So if your slope here is positive, meaning that it's going up, you want to go the opposite way because you are minimizing the loss function. So, with this simple formula, it would just update, 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 and then sort of like converge until the very end. And we talk about, this fancy back propagation. But for now, think about it, just a more efficient way to do gradient descent. And it usually just happen inside whatever, deep learning framework that you're using, PyTorch or TensorFlow, it will happen under the hood. But that's the most, computationally heavy thing that's being done on the GPU. So, this is the backward pass. It was sort of like get the gradients one step at a time, one layer at a time from the bottom to the very beginning. Cool. And so last we end up somewhere, we are talking about how we can solve this, local minimum and global minimum issue where you have this like complex loss landscape. And there are so many local minima, and so gradient descent will lead you to those local minima rather than the global optimum one that we are looking for. So we talk about you can use an optimizer with adaptive learning rate, use a stochastic optimizer, we haven't talked about it, and make it smoother. But basically, for the optimizer, people nowadays, usually how we do is just to try Atom first to see whether it works. So it leveraged two things, the Atom optimizer that we are usually using is that one is momentum. So, it's sort of like when you throw a ball to some dip, then it will still keep moving toward that. So it allows you to sort of like get out of those local minima that you don't want, and so allows the model to explore around. And it also leverages gradient-based adaptation so that it will look at different dimension, which dimension is, if the slope is lower, then you try to increase your learning rate on that. Cool. Any questions on the things that we talked about last week? Well, I think last week we finished at somewhere at the adaptive learning rate thing. So this week we talk about start stochastic optimizer. But the idea of stochastic optimizer is quite straightforward. So the idea is that what we've talked about is that at each simple step you sort of like compute how far away is that for this particular example. So, in deep learning, how we do it is rather than, just doing one simple samples at a time, but rather we are trying to sort of like aggregate the gradients from different training samples. We have a much better, well, don't have it. So, the default thing to do it is to sort of like compute the average gradient on the whole batch of examples. So, if you have a data set of, 100, 1 million samples, then you just compute one gradient based on that 1 million samples. So it will lead to, very nice gradient descent paths where you just compute, the gradient over a million samples and update it with the best gradient estimates that you have. So stochastic gradient descent is a bit different. So basically we estimate the gradient using just one random training sample. So now what it does is that look at your training data set, you just grab one of it. And then if it's a guitar sound and you just train your model, predict your model output and it says it's a, organ sound instead. So that you just optimize your model so that it do better on this guitar sample. So gradient descent, if you are doing the typical way, the batch gradient descent, then it's like, look at all these samples. You have, violin samples, you have guitar samples, you have, organ samples, and look at all of them, try to see what's the best ways to optimize it. So that's the difference between stochastic gradient descent versus gradient descent, is that gradient descent is that, you look at, a million samples, so that you get one single, gradient update. But stochastic gradient descent is that you just look at one single sample and try to guess where the gradient is going toward. So, it will lead to some very shaky or unstable updates for your model. But the benefit of it is that you get more updates and you can compute much easier. So when n is smaller, it's you won't see the bigger difference. But when n is a million, it's meaning that you just go over your data set, a million samples, and you just go get one single update. So to go through, typically nowadays you need at least 100,000 steps to train your model, or a million steps to train your model. So it doesn't make any sense if you want to do the traditional batch gradient descent. So you can speed up the computation of the gradient, and at the same time, you also add some randomness to the gradient descent algorithm so that you can sort of like, look at this, you can sort of like jump out of those, bad local minima. Cool. So this is sort of like the loss function you will see. This is like a visualization what's going on, but this is typically what you will see. So at the left is the gradient descent. If you do perfect, gradient estimation, it looks like this. But this usually never happen whenever you are doing a deep learning project. It would look something like the right-hand side, at each step, because you are guessing what the gradient is. So all the gradients will be very unstable, jumping around. So usually what we've done in practice is actually something between them, that, what we do is to grab several random training samples. So now, you have a million different instrument sounds, but now instead of like just compute the gradient on the whole data set, that's, batch gradient descent. And on the other side, we have stochastic gradient descent, where we just, grab one of the sample. Now, mini batch gradient descent is something in between, where we choose, say 16 or 32 or 8 samples randomly, and then we compute the gradient and then update it. So, mini batch gradient descent is typically what's being used in practice. It's sort of like somewhere in between them. Gradient descent is that it doesn't make much sense because, to get each one of the update, you have to go through the whole data set. It just infeasible in practice. And for stochastic gradient descent, if your training loss is like this, at some point, even you have trained it for, a million steps, you have trained it for hours. But at the end, you will sometimes, if you're unlucky, you sometimes get these, very bad model because you are your model training trajectory is too unstable. So mini batch gradient descent helps to sort of like get the best out of the two worlds. You don't have to compute, the gradient based on the whole data set, but you have the benefit of, speeding it up, but at the same time, reduce that instability. Well, when you do it in PyTorch, it's just basically that batch size. So, pretty much you will see some batch size in your deep learning training script, and that's what batch size mean. So it means that for each step of update, how many samples are you looking at? So the larger the batch size, you sort of get a better estimate of what you are optimizing your model. And when the batch size is small, you will get, worse prediction, so that it will become more unstable. And if your batch size is larger, then you get a much smoother training trajectory, but you are, sacrificing the speed of training. So you always need to figure out which one is the best. Cool. So this is sort of like a figure to show you what's the effects of batch size. So here we see, different loss curve for different batch size. So basically on the x-axis is the epoch. So epoch, you can think of it like how many times you go through the whole data set. So one epoch is defined as a full run of your data set. And the y-axis is a loss function. So if you just look at this figure, you will sort of like arrive at the, a weird, it's like a weird conclusion where you want a smaller batch size. But that's not the case in this case, because, look at each single epoch. The blue one, which is the batch size 32. So, if your data set is, think about it like 1 million, then you have like 1 million over 32 batches in the blue case. But for the red one, it's like 1 million over 256 batches for that particular setup. So, the blue one will go through a bunch more, 4 times more weight updates than the red one. And that's why, the blue one leads to a better, a lower loss. So this is sort of the idea of understanding batch size. It's not like batch size is the bigger, the better. The bigger, the smoother the training progress. But at the same time, if you have a smaller batch size, you can get more updates over the time. Any questions on batch size? So the biggest takeaway is that this thing do two things. One is to introduce some randomness into your training algorithm, that you are picking different stuff at each iteration. But second, you speed up the training. Cool. So the final one is much easier. Can we just try to make it smoother? This is basically what can be done. So, we talk about that skip connection, which is the highway stuff. Without doing that highway connection, what you see, that loss function will be something like that. So this is the benefit of that skip connection. So once you have these highway stuff going on, it's like jump every 2 layers that you jump to it. So, this the quickest way to go from the input. So this is the input, that is the output. So the quickest way to go to the output is that you don't even go through any of these layers. You just follow the jump. You can sort of like just go it all the way to the end. So, these different stuff actually make it much easier to, make your life easier, because your model become much smoother. Cool. I guess that's all we need for now. Let's jump to the other slide deck. Cool. Okay. Well, we've talked a lot about the details of optimizer. For most of the time, you will just be, in PyTorch and, fine-tuning different parameters. But let's sort of give you an idea what those parameters is doing. You will have a whole lot of parameters that you can choose from. But more importantly, this is a very important concept in deep learning, where we will talk about training set, validation set, and test set. So that's the concept. So to start with why we want to do this training validation testing, we should think about what does it mean by, this two term in distribution and out of distribution. So this is sort of the core concept of, machine learning. So think about that you are training some, animal classification algorithm, and this is your training data set. So when you're thinking about doing this, machine learning model, what you want to know is that whether some item is of your interest. So think about these. Are they part of your distribution that you want to know? Do you want to model these, images that, slightly different from your training data, but, it's not so far away? So, likely, yes, that you want to sort of like train on these, standard images, but, you hope your model can sort of like generalize to, slightly different thing. So in this case, we will be thinking about, training on these things, but test on, slightly different thing. But, you can also think about, animal classification case where, well, we just extend our data set to cover a bunch more different flavors of, animal images. So in this case, if we are training on the whole set of these different images, you have like bear in its, different positions or gestures, then now the question would be, does the, somehow blurry-ish images count as your distribution? Do you want your model to be generalized to these, potentially, bad phone capture of these images, or maybe it gone through some compression algorithm that doesn't that sort of like break the resolution of your images. So, if you're thinking about animal classification, what do you mean by animal classification? Does it always need to only work on, high resolution images, or if you are just taking your phone and just do it, sometimes it's blurry because you are shaking your hands. Does your model need to cover that? So again, now in this case, you have this like training distribution, and now these, tricky part would be your test distribution. So, again and again, you can always, when you're sort of like trying to define what you want to do in machine learning, you have to think about, what are the distribution that you are actually trying to model. So, even if you sort of like do some data augmentation, try to, get all the image and you get some sort of like it's blurry version of it, and then add it to your training data set, there will be always something out of your distribution. Cartoons, or even like art, like, or art rendering of the some animals. So your model cannot always cover all the distribution that you want it to be covering. So you always have to think about, in machine learning, your data sets sort of define what can be done with your model that you train. So that's the core concept, and that's what leads to why we need training, validation, and test distribution. So the idea of machine learning is that we want to make the training distribution closer to the target distribution that you are testing. So that's the core idea. If you want to make your animal classification model to work on blurry images, then the best way to do it is to try to make your training data be that distribution. Your training data should include some blurry images of some animals. If you want your model, say, in the NSYNC data set case, if you think about a version of NSYNC that doesn't have any velocity difference. You just grab a bunch of single shot musical instrument that always play in, the maximum value. Then your model will not generalize to, a softer sound of it. So the only way to make it work is that make your training distribution closer to the target distribution. So, to do it, you have to sort of like define your target distribution first. So that's the most important thing when you are doing deep learning and machine learning. Think about what you are actually modeling. And then now we have this training test and training validation test idea of doing this toward our goal to sort of like model the target distribution. So, these are two ways to make it work. You can collect a diverse data set covering different parts of the target distribution. You can apply data augmentation to fill the gaps in the distribution. Now, what do we really want? Time to think about it. Do we want good performance on the training samples? Or do we want good performance on unseen samples in the target distribution? Or do we want good performance on out of distribution samples? What do you think?
Second one,
Why?
what's the point? We obviously want good performance on training, but real life isn't training. You don't want like 100% accuracy on.
Yeah, exactly. So, we don't necessarily need to have good performance on the training sample because we already have the answer. It's like you have this animal classification data set, well, you do perfectly on your training samples, but well, we do have the ground truth. What's the point? But why didn't we want, out of distribution samples for good performance?
Because target distribution, we only care about the target distribution. That's we don't care.
Well, I would say we care about out of distribution samples, but technically in the context of deep learning, all we can do is try to make your model to do better on out of distribution samples, but there's no guarantee it will do better. So this sort of, first, we already have their answers, so we don't necessarily interested in those training samples. You have a big data set of a bunch of instrument and their labels. Why should you care? Your model can do 100% accuracy on those if you already have the answers. You're interested in trying to make your model work on some of the new stuff that you want to model. So that's exactly the second one. That's something we can do and we should care for. That is like unseen samples in the target distribution. So, if you want to train some model, that means that you want to apply it on some new, unseen samples that you are interested in using. And finally, we also want good performance on out of distribution samples, but that's, hopefully, but not guaranteed. So, some of the machine learning algorithm that people are researching on is trying to do this, try to figure out some models that, can sort of lead to better out of distribution generalization performance, but it's not guaranteed. It's just hopefully the model will be doing better. So, the goal here is that how can we achieve good performance on unseen samples in the target distribution? So that would be the key of this, the following slides. So before that, we should think about this, overfitting and underfitting. So maybe you've seen something like this, if you're given a bunch of samples where the blue ones, where's my cursor? The blue ones, and you are trying to model that. So, you have the blue one is your prediction. So this will be a very good fit. But if you are making your model too simple, then in this case, the blue one is so far away from your actual, samples. So this is not a good fit in. We will probably agree. But at the same time, at the right-hand side, you have this cool shaky function that sort of like perfectly go through all these samples, but it's sort of like too complex that it doesn't actually match the, the underlying, the underlying distribution that you are getting. So this is sort of the idea of why we should have, training, validation, and test, is that what we are actually aiming is trying to figure out what's a good fit. We don't want something that's, too complex, even though it leads to the best, loss value. But we also don't want something that's too simple, that doesn't capture the complexity of our model. So, this is like model 2 in expressive, and at the right is model 2 expressive. So that's the 1D case, but you can also think about this, if you have some data set like this, what you will guess, what the data set is like, you can sort of like just do this linear thing. And well, it's not bad. I mean, at these, at the right-hand side is mostly green, and at the left-hand side, more blue than green, but it doesn't necessarily capture the complexity of the data set. But you can also do this, you do this very curvy stuff, but, it doesn't make much sense in general for our understanding of what this data would be like. It could be right that your data set is like this, but, generally what we are aiming for, it's not something that complex. So, a good fit would be something like this. It pretty much cover all the things that we need, but, it also have some, errors that's acceptable at the boundaries. So this lead us to this trend test split. So whenever we are doing machine learning, we don't want to train our model just on all the training data that we have. Because, once you train it, you have no idea how it works on, some new unseen samples. So how we do it is that, given a bunch of training data, we always sort of like split them into two groups. So one is the training distribution, and the other will be the test distribution. And the ratio differs sometimes, but usually is 80-20 or 90-10. So, basically you leave 10-20% of test set to test your performance. So now what we are trying to do is to see what's the best we can do by using this, only 90% of training data, try to see what is the best performance that we can get on this test set. So that's the setup. So, one important concept here is that test set is just an estimation of the test distribution. We create a test set. It's like artificially created stuff because we want to estimate the performance when the model is applied to an interested distribution. So, sometimes you will even see plenty of different test sets, and each test set is like trying to test, different things that you are interested in. So test set is a concept in machine learning. It's rather than, something. It's not the golden standard, I guess. And especially in the case when you are trying to apply it into creative and artistic application, then test set has become less and less important because test set is just an estimation of the test distribution that you're interested in. And by no means you can actually estimate it correctly. Anyway, so this is the idea where you want to just try to use this training thing and try to test it. But as we talk about, that overfitting thing, if you train the model just using the whole training data set, there's no guarantee it can work better on the test set because, it's the best model for your training data set only. So the idea of training validation test split is to even, break this training data set into two. So one is the training set, one is the validation set. So typically how we do it in deep learning or machine learning in general, certain type of machine learning is that we will train our model, whatever neural network, on the training data set. And so we will optimize our model into, different versions of that. So each of these, neural network could be with different, architecture, different learning rate, different optimizer, or, different ways of augmenting your, training set. You can do, include blurry version of your images, or you don't do it at all. So there are different ways. And then once you've done with the training, you get a bunch of different candidates. You select the best one on the validation set. So now you select based on the validation set performance. You try to figure out which one is the best out of this various different candidates of your models. And then finally, you test it using your selected models. Questions here? So why should we do validation? What's the goal of doing validation? So, the goal is the same. As we suggest, the goal of machine learning is to try to, do the best on getting the best performance we can in unseen distribution in the target distribution. So validation set is a way to sort of like prevent overfitting and underfitting, so that, when you train on these, these samples, you sort of like get the best out of the training set, but it doesn't guarantee the best, performance on some of the unseen samples. And that's why we need the validation set so that, you can get the best performance of it. Yeah. So usually, it depends on the scenario. If you're doing some challenge or, you're doing machine learning competition, there will be test set, but in real life, there's no test set. That's the biggest myth of machine learning, is that people always think about, well, there are some test set, we should do the best accuracy on the test set as possible. But in real life, there's no test set. Test set is just artificially created stuff. Cool, but test set is still nice. So usually how we did it, if you look at some machine learning competition, is that there will be some organizer. They have their data set and they will leave like 10% of their test set into their private their some disk. They just store it and they will not let you know what their test set is, and they will release the other 90% to you as something you can do your training. So you can grab those 90% and then you just do the training, but there's no guarantee you will do better on the test set. And that's why we split the training data set into two parts, so that you have training set, you have validation set. And so you sort of like do this, mock test scenario where you just train on part of it and then try to see if it worked well on the other like 20% of these unseen samples from your training model, so that you sort of get a sense how your model generalized to different stuff that it hasn't looked at before. And hopefully at the end, that will lead to a model that worked better on the test set. So that's the idea of how these things work. Yeah.
About set like actually improve your model at all, or does it just like give you insight as to how your model is doing based on the training?
I would say both. It's like define improve. So if your goal is to do perfectly on the training set, it's like you should include everything.
Yeah.
But that's not our goal.
Yeah.
Our goal is to see whether we can do it on some of the new image that the model hasn't seen. So that's why we need validation. So validation does improve that, because without having validation set, you will get a model that do perfectly on these, but catastrophe performance on the test set. So that's not something we want. So validation, I would say both objective. One is try to select the best, try to sort of like mimic that behavior, what's the best model that will generalize. But at the same time, it actually does improve the performance by selecting the one that actually could generalize, rather than those are perfectly on training set, but who cares? I think the next slide will sort of give you that sense what it is. So usually what we are training these model, you will sort of like plot this training loss function curve. So this is exactly what you want to do in homework 3. So this is sort of like in most of the machine learning papers, if they are actually working on machine learning, they will usually have this figure. So what you'll see usually is something like this, that your trending loss will just go down and until it will just keep decreasing, because the gradient descent idea is that whenever you stand, you just look at where you can sort of like improve. So trending loss will sort of like never increase in some sense. If you're using stochastic gradient descent, sometimes there will be spikes, but generally trending loss will just keep going down. But validation loss is not the same. So validation loss, usually you will see at some point it will reach a minimum and it will go up. So this is when we talk about overfitting. So before this step, this magical steps, trending loss and validation loss, they are both improving. So think about this case is that when you are training on this training data set, it will just do better on these images. But at the same time, the model will start to look at what's cat, what's dog, and it will also increase your performance on the validation set. But at some point, once you've done too many training, now the model will be doing the opposite. The loss will become different paths. The validation loss will start to go up, and the training loss will still keep decreasing. And that's when the case overfitting is happening. That means that you are doing better on your training set, but your model now only knows how to do your training images. It never knows how to generalize to other cat and dog images. So that's not something what we want. So this is where the point that you should stop doing your training set training. So you can think about that as sort of also fall into this training validation test scenario where you train your model over different epoch or different training loss. So you get a bunch of different models here, and they are doing great on the training set. And even the last one is better than the previous one. But that's not what we want. We should use validation set to look at what's the best model that we want. And that's the one that's the lowest in the validation set. So that's sort of the idea how you do it. Questions? Nope. So this is what you want to get in homework 3. So we can look at it. So homework 3 at some point, you just press Shift Enter all the way down to this part. This is the huge training loop. You will just go through the data set, and select 32 samples into your model, and then you do your model prediction. So you guess what you grab a bunch of mass spectrogram, get the prediction of that, and then you sort of like compute how far away that prediction is to the labels. And once you have this loss, you will do this loss backward. So that's the what's that? Back propagation thing is doing. And then you do optimizer dot step. So this is the gradient descent. So this is the back propagation. You compute the gradient, and then you do optimizer dot step, which is trying to do that gradient step, so that you try to update your model weight so that it do better on the loss function. Anyway, what you'll see is something like this. This is the first epoch, second epoch. But anyway, at the end, where you will see is something like this. So you have validation loss that's sort of like stuck here. And then you have training loss just keep lowering. But what you want is actually the lowest thing that work in your validation set. This is a real life scenario. So you can also look at things behind. The training loss is actually the gray out stuff at the back. So this one is actually already smooth version of the training loss. So usually training loss is super noisy, and you have to sort of like do moving average to get a more smoother view of that loss. But anyway, this is a real life thing. We did some tricks so that validation loss won't go up too quickly. But anyway, the idea is that training and validation loss doesn't always moving toward the same direction. So, this is, the perfect scenario, but of course, in real life, it never happened this way. So sometimes you will see something like this. So what does this mean? If you're training something and, your training loss just keep going down and somehow your validation loss just stay up there. It's like, well, what's going on? What would be the reason of this?
Still not overfitting.
That's one thing, but even let it do a million step, will it overfit? Well, no, because they are still far, far away. There's a constant gap. It will never overfit. So this seldom happen. So this usually happen when you have, underrepresented validation samples. So think about the extreme case. Sometimes people are like, well, reserving 10% of our data as validation set is sort of a waste of our training data. We should do 99% versus 1%. And this is usually what you get,
So it's still like overfitting because it's using so much for training.
It's unclear whether it's overfitting. You can still try to measure how good the model generalized on that 1% of data set. But this is something you will see when you are doing that, is that 1% of data sometimes doesn't, if your data set is very imbalanced, say, it doesn't even cover one of the samples in your data set. So, this is not something that bad, but it just usually means that your, validation samples are, unrepresentative. Because what you want is that, your training loss and validation loss should go sort of like close together, and at some point they diverge. But this is sort of like they just never be the same starting on day one. So that usually means that, validation is so different from your training set. One case is that, you only choose 1% of validation, but sometimes it's that you did something wrong in your training validation set setup. Sometimes you did something wrong in your sampling algorithm that, say, for the instrument case, that you have 11 instruments and you somehow did something wrong, then you get the training on the 10 instrument at all, and you put all the other instrument on this validation set. So that will be something that's happening. It sometimes happen. It seems unlikely, but sometimes you see this. Usually that means, at least, your validation set is not representative to your training set. So, the way to solve it is, well, increase the size and diversity of the validation set. But the key is, so that is, part of the training set and also part of the target distribution they're interested in. And you can also apply cross-validation. That's something we didn't talk about, but it's just sort of like divided your data set into, using this part of, 80%, 20%. So, but cross-validation, do a very quick overview, is that, say you have a huge data set, and you say do 80%, 20%, and then the other time you just do, these part as training and these part as testing, and you just did different way. Say you just need these 20% as your validation, and these will be training. So this way you are doing cross-validation is that, you just change your validation over time so that your model can still learn from the whole data set, but you sort of get a sense of, how the model works. And this is another case. This would be the case that's, it's not overfitting at all. So your model is just still far away from modeling your models. So usually you can just keep it training, and at some point you will see that validation loss will go down. So this is funny because this is actually some of our recent models, those big language model, they are actually into this, is that they actually hasn't converged. So many of the GPT model in the early days, I don't know whether they have converged nowadays, but some of the GPT models, they actually hasn't converged. So, it's something like this, that, if you keep training it, at some point, you will see that validation loss start to stuck or go up. Then that's where we sort of, that's the best your model can do. This is like, well, it's still going on. The model can be better, but if you don't have any more time or resource to train it, then, that's the best you can do so far. So train it for most steps, increase the learning rate. But sometimes you will still see this. This will be unfortunate. Basically means that after this point, you're sort of wasting your time, keep training it, because, at the very first, once all the steps, you sort of like stuck here, that your model just, it just do better on your training set, but it doesn't actually improve your validation. So that means that your model will be doing better on your training set, but you don't necessarily care about it. You care about its test performance and test validation performance. So, possible solutions, reduce the model size. So this is interesting because, the bigger your model is, it will tend to overfit more easily. So your model size had to somehow scale with your data. So if you don't have enough data, if you want to build a large model, it doesn't make much sense. It will quickly overfit. And you can apply dropout added regularizer, but we will talk about those later. But the keys, I guess, here is never train or select your model on test samples. As you can see that we never talk about test set. Test set should be something that you will never look at it until the last minute, that once you've done everything, you just look at how it works on test set. And, test set is usually for computation, competition, or, paper publishing case. So usually you shouldn't be selecting anything on the test set. And, even though we talk about validation set, but don't over select your model on the validation set. This is sometimes some of the mistakes people make is that, you over select your model on the validation set. Somehow you also overfit on the validation set. And the best ratio most commonly is 8-1-1. So 80% for training, 10% for validation, 10% for test. Sometimes you can do 9, 0.5, 0.5, depends on how large your data set is. But for smaller data set, you actually want larger validation and test set. So this is sort of like counterintuitive. It's that, you have smaller data set, you should keep more on the training set, but it's actually opposite. The smaller your data set is, you should have more ratio on the validation and test set. And what you can do is to do cross-validation so to improve that. Cool. We still have some slides, but I guess we can stop there. And on Wednesday, I'll finish them and go through homework 3. And hopefully you can start training your first deep learning models.